Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. In the last lecture we studied direct matrix updating method for finite element model updating. In this lecture we are going to study iterative method of model updating using model data. So there are two major differences between the iterative model updating and direct matrix model updating. One difference is related to what is updated and other is related to the formulation of the method. So in the iterative method, the chosen uncertain parameters of the FE model, they are updated to minimize the difference between the measured and FE model data. So in the iterative method, the direct entries of the stiffness and mass matrices, they are not updated. What is updated are the chosen parameters of the model, and these parameters indirectly affect those system matrices. Let us say we have chosen q number of parameters that we would like to update during updating. So we can form a vector of updating parameters. So therefore it is a vector p here, which is the vector of updating parameters, and it consists of parameters p1, p2, p3, pq. So these parameters could be related to the material properties, the joint properties, damping properties. So other input parameters of the model, all of them can be taken as the updating parameters. So the second difference is related to how the updating parameters are determined. So in iterative model updating using model data, the parameters are determined based on a linear relationship between the model data and the updating parameters. And because the linear relationship is approximate in nature, so the parameter estimates that are obtained from this linear relationship, they are also approximate, and that is why the parameter changes need to be improved over the iterations, and that is why the method is iterative in nature. So let us look at the formulation of the iterative model updating method based on model data. So let us say at the beginning of the kth iteration, the parameter vector is denoted by pk minus 1. So this is pk minus 1, which represents the parameter vector at the start of the kth iteration. So in the kth iteration, then we estimate what should be the change in the parameters, that is represented by delta pk. So delta pk is the estimate of change in the parameters in the kth iteration. So at the end of kth iteration, the parameter vector gets updated, and that is denoted by vector pk. So therefore pk is equal to pk minus 1 plus delta pk. It basically defines how the parameter vector is updated from iteration to iteration. But now the question is how delta p is determined. So delta p is determined by linearizing the eigenvalues and eigenvectors with respect to the updating parameters. So eigenvalues and eigenvectors are nonlinear functions of the updating parameters. We linearize them using Taylor series expansion, and therefore the linearized equation for the eigenvalue can be written like this. So here the subscript x represents association with the experiment, a represents association with the FE model or the analytical model, subscript I represents the ith model data, that is in this case lambda xi represents the ith experimental eigenvalue, lambda ai represents the ith FE model eigenvalue. So subscript j represents the jth updating parameter. So here the eigenvalue lambda xi is linearized about the FE model eigenvalue at the start of the iteration, and this quantity is the change in the eigenvalue because of changes in different updating parameters. So because there are q number of updating parameters, therefore the eigenvalue will change because of change in each of these updating parameters. So this is the first order linear approximation of the relationship between the eigenvalue and the updating parameters. So a similar relationship now can be written for the eigenvectors, and that is this. So here the left hand side represents phi xi, which is the ith experimental eigenvector, and that is written using the linear approximation as sum of the ith analytical eigenvector or FE model eigenvector at the beginning of the kth iteration or at the end of the k minus 1th iteration, plus the change in the eigenvector as a result of change in the different updating parameters. So, in this way we get these two relationships for the ith eigenvalue and ith eigenvector. And if we are using m number of eigenvalues and eigenvectors for the formulation, then we will have such equations for all those m eigenvalues and eigenvectors. So, all these equations we can combine and write a compact matrix representation of these equations. So, we get this matrix equation. So, on the left hand side what we see, it consists of the difference between the experimental and analytical or the FE model eigenvalues and eigenvectors. On the right hand side we have this coefficient matrix which consists of the derivatives of the eigenvalues and eigenvectors with respect to different updating parameters. And then we have this vector of changes in the updating parameter, which is the unknown. So, here the coefficient matrix is known and the vector on the left hand side is also known, because we know the experimental eigenvalues and eigenvectors, and we also know the parameter vector at the beginning of the kth iteration. So, based on that parameter vector we can solve the eigenvalue problem based on the FE model and find out the analytical estimates of the eigenvalues and eigenvectors. So, those are the ones which are appearing on the left hand side of this equation. So, now here to find this coefficient matrix we need to know the derivatives of the eigenvalues and eigenvectors, and they can be obtained using this relationship. So, you can see this is on the left hand side we have the derivative of the ith FE model eigenvalue with respect to the jth updating parameter, and this requires ith FE model eigenvector and the stiffness and mass matrix of the FE model and the ith eigenvalue. So, these quantities are all known for the current iteration, and that is why we can find this derivative. Similarly, the derivative of the eigenvector with respect to the updating parameter can be found out using this relationship. So, all the quantities appearing on the right hand side of this equation, they are known for the updating parameter at the beginning of the current iteration. So, by calculating these derivatives, this matrix equation can be set up. So, this matrix equation can be solved for the unknown parameter vector delta p, and then the parameter vector can be updated to obtain the new estimate of the parameter vector, and in this way the method can be iteratively implemented till the convergence is obtained. Now, it is seen that if the parameters which are updated, they have different orders of magnitude. For example, if we are updating, let us say, modulus of elasticity, and let us say thickness of some element we are updating. So, these parameters have very different orders of magnitude, while E has its absolute value is very large, while the thickness generally is small. So, this will affect the conditioning of the coefficient matrix. So, therefore, we can modify these equations in order to improve the condition of the coefficient matrix, and for that purpose we define fractional correction factors. So, what is the fractional correction factor? So, let us define the fractional correction factor for the jth updating parameter. So, it is the ratio of the change in the jth updating parameter at the kth iteration divided by the absolute value of the jth updating parameter at the beginning of that iteration, that is p j k minus 1. So, this is nothing but delta u j k, which is the fractional change in the jth updating parameter at the end of the kth iteration. So, that is referred as fractional correction factor. So, fractional correction factor conveys the change in the updating parameter in terms of fraction. For example, if the value of delta u j k is say 0.1, it says that there is a 10% change of the updating parameter from its present value. So, the fractional changes in different parameters irrespective of their absolute values, they become easily comparable. So, this helps to improve the condition of the coefficient matrix. Another observation is that the eigenvalue error is generally much larger in terms of its magnitude as compared to the eigenvector error. Therefore, the eigenvalue equation is divided by the corresponding eigenvalue. So, now we incorporate these changes in the matrix equation we got for updating, and therefore, the modified matrix equation takes this form. So, here we see now the unknown vector is no longer the vector of absolute changes in the updating parameter, but it is a vector of fractional changes in the updating parameter. So, let us represent this equation as matrix S multiplied by vector delta u is equal to delta z. So, here S is nothing but a coefficient matrix, and this coefficient matrix consists of derivatives of eigenvalues and eigenvectors, and they also can be said to represent the sensitivity of eigenvalues and eigenvectors with respect to different updating parameters, and that is why this coefficient matrix is often referred as sensitivity matrix. Delta u is a vector of fractional changes in the updating parameter, and delta z is the vector of differences in the eigenvalues and eigenvectors corresponding to experiment and FE model. So, this equation represents a set of simultaneous linear equations in unknowns defined by vector delta u. So, here the matrix S is of the order 1 plus n into m into q. So, number of columns in matrix S are equal to number of updating parameters, and the number of rows in matrix S are equal to number of modes multiplied by 1 into n, where n is the number of elements in the measured eigenvectors. So, that is nothing but the order of the sensitivity matrix. The order of the delta u vector is q by 1 because there are q number of updating parameters, and the order of delta z is 1 plus n into m into 1. Now, it is desired that these simultaneous linear equations, they are overdetermined, which means that the number of equations are more than the number of unknowns in the vector delta u. That will ensure that the estimate of the vector delta u is physically meaningful. So, these overdetermined equations then can be solved using least square technique, and we can obtain a least square solution for delta u vector. So, once we solve these equations, we get delta u. So, this delta u is nothing but delta u k, which is the vector of fractional changes at the end of kth iteration. From delta u k, we find delta p k, which is the vector of absolute changes in the parameters at the end of kth iteration. From delta p k, then we find p k, which is the absolute values of the parameters at the end of the kth iteration, and from p k, then we find the mass and stiffness matrices based on p k, and then by solving the eigenvalue problem, we get the new estimates of the eigenvalues and eigenvectors, and then we again set up this updating problem, and then we solve for new values of delta u for the next iteration. So, in this way, this process is repeated in an iterative manner. Now, we can also find the cumulative change in any updating parameter at the end of kth iteration. So, let us say u j k represents the cumulative change in the jth updating parameter at the end of k iterations. So, that can be determined by the values of delta u for the jth parameter which were obtained over all iterations. So, delta u j 1 represents the fractional change in the jth updating parameter at the end of first iteration, and delta u j k represents the fractional change in the jth updating parameter in the kth iteration. So, from all this we can then determine the cumulative change, and that is given by this equation. So, the difference is that delta u j k represents the fractional change with respect to the absolute value of the updating parameter at the beginning of the kth iteration, while u j k represents the cumulative change in the jth updating parameter over all the iterations. So, it is with respect to the value of the jth updating parameter which was there in the initial FE model when the updating iterations were started. Let us now take an example of updating with the iterative method using model data. So, again we are going to consider the cantilever structure we considered in previous studies, and we are again going to have a simulated study where the experimental data is generated from another FE model of the structure. So, this is the simulated experimental structure, the cantilever beam fixed at one end. So, in practice, because the ideal fixed end cannot be realized, the flexibility has been simulated or modeled by using a torsional spring at the fixed end. So, the modulus of elasticity of the beam material is taken as 1.8 into 10⁻11 Newton per meter square in the experimental structure, and Kt is taken as 2500 Newton meter per radian. Now, let us look at what is the initial FE model that we are going to update. So, initial FE model, the value of modulus of elasticity is the standard value, which is 2 into 10⁻11 Newton per meter square, and torsional stiffness is taken as 4166.7 Newton meter per radian, and this is the initial FE model that will be updated. So, therefore, the initial FE model contains inaccuracies associated with the material property and the boundary condition. So, now we perform updating with the iterative method using model data. We take E and Kt as updating parameters, and then we are going to use the 4 measured eigenvalues for updating. So, what we do, first we compute the Mach matrix, because we need to establish the correlated mode pairs so that the corresponding eigenvalues can be compared. So, we first compute the Mach matrix. So, we have 4 measured eigenvalues. So, we use 6 eigenvectors from the FE model, and then find a MAC matrix between the 6 FE model eigenvectors and 4 measured eigenvectors. So, that gives a MAC matrix of 6 by 4. So, it is easier to visualize this MAC matrix in the form of a 3D bar chart. So, let us see a 3D bar plot of the MAC matrix. So, you can see here we have these 4 experimental modes, experimental eigenvectors, and then we have 6 analytical or FE model eigenvectors, and on the vertical axis we are showing the MAC value. Now, from each row of the MAC matrix we see which is the highest value, and then the corresponding modes from the experiment and the FE model are considered as correlated modes. So, from this MAC matrix we get correlated mode pairs, and these correlated mode pairs are found to be 1 1, 2 2, 3 3, 4 4, right, which means the first mode from the FE correlates with the first mode from experiment, second mode from FE correlates with the second mode from experiment, and so on. So, once these correlated mode pairs are established, now we can compare the corresponding eigenvalues. So, now with this information we set up the updating equations and we perform updating iteratively as we discussed. So, this is the plot of fractional correction factors in the 2 updating parameters over iterations. So, this plot shows that how these fractional corrections they converge over different iterations. So, it has taken now 6 iterations for the method to converge, and at convergence we see that the cumulative fractional correction factors, that is vector u, is minus 0.1 and minus 0.4. So, minus 0.1 represents a 10% reduction in the modulus of elasticity with respect to the initial value of the modulus of elasticity in the FE model. Similarly, minus 0.4 indicates that the updating method has predicted a 40% reduction in the torsion stiffness with respect to its value in the FE model. So, the final absolute values of E and KT are obtained as this. So, E is found to be 1.8 into 10 to the power 11 Newton per meter square, and KT is found to be 2500 Newton meter per radian, and these values are found to be exactly matching with the values that were simulated in the experimental model. So, this shows that the iterative method has been able to identify the correct values of the uncertain parameters. So, this iterative model updating method using model data is also referred as inverse eigensensitivity method, because here the updating equations which are solved to obtain the parameters that involves a sensitivity matrix and whose pseudo inverse needs to be taken in order to obtain the estimate of the updating parameters, and that is why this method often referred as inverse eigensensitivity method. Let us look at what are the advantages and limitations of the iterative method. So, one advantage of this method is that the method allows the choice of updating parameters. So, it gives the control over the scope of the changes during updating. So, here because the parameters are to be decided by the user, so the engineering judgment can be used to decide what parameters should be updated during updating. So, one would like that the parameters which are chosen they correspond or represent the modeling inequalities which are present in the model, so that when the updating of these parameters is carried out, those inequalities are reduced in the model when the matrices are updated. So, that is the advantage of this method, that the parameters or the changes which would occur during updating can be controlled by selection of the suitable parameters. Other advantage is that this particular formulation which we discussed in the lecture that allows use of incomplete data. No model reduction or expansion of mode shape is to be carried out for implementing the method. For example, to find a eigenvector error, only the degrees of freedom corresponding to the measured eigenvectors can be used for finding that difference or the error. So, no mode shape expansion is required in order to implement the method using eigenvectors. Of course, one limitation is that in some cases there may be issues of lack of convergence, the parameters may not converge, and also the sensitivity matrix may face ill conditioning in some cases depending upon what parameters have been chosen and what data has been used for updating. So, let us try to look at what is the motivation for stochastic FE model updating. An FE model of a structure or a system is constructed based on its nominal design. Nominal design prescribes nominal values for different design variables, and these nominal values are unique, they are deterministic, and that is why the input parameters of the FE model are also unique. So, that makes the FE model a deterministic model. The predictions which are made using such a model are deterministic, they are single valued. However, several samples of the structures manufactured based on the nominal design, they will have variability associated with them. So, it is seen that the dynamic characteristics of different samples which are manufactured based on a given nominal design, those dynamic characteristics, they are not identical for all the samples, but they have a variability. So, what we see is that the FE model based on a nominal design is unique, but the samples which are made or manufactured based on that nominal design, they are not unique, they have a variability. The variability may be associated with joint properties, with the metal properties, with the geometry, right. So, all these factors lead to variability in the dynamic characteristics of these samples. So, this situation is depicted using this figure here. So, you see we have a certain nominal design of a product or a system. So, based on that nominal design, we make this FE model, and this FE model is a deterministic model, and therefore, the model parameters which are predicted by this FE model, they are deterministic, they are single valued. So, for example, one particular model parameter is shown here, and that has a unique value shown by this vertical line. However, different samples which are made based on this nominal design. So, these are the different physical samples based on the nominal design, and if dynamic test is conducted on these samples, right, then we get model parameters corresponding to each sample. So, this is the model parameter for this sample, this is the model parameter for this sample, and so on. And when we compare these model parameters for different samples, what we see is that these model parameters have a variability, they are not identical, and therefore, these model parameters can be represented by this statistical distribution, which shows that the model parameter is not single valued, but it has a statistical distribution. So, this shows that the FE model is not able to therefore predict the mean value of the this distribution, and also it is not able to predict the variability or the covariance associated with this distribution. So, the deterministic FE model predictions, they may not match with the mean values of the distribution, and they also may not be able to predict the variability or spread of the distribution. So, therefore, what we would like is that the FE model should be able to predict not only the mean values of the distribution, but also the variability of these distributions. So, that involves determining what is the variability associated with the input parameters of the FE model. So, that needs to be determined, then only the FE model will be able to predict the distribution of the dynamic characteristics. So, this has led to development of stochastic FE model updating. So, stochastic FE model updating treats the parameters of the FE model as random and updates their mean and covariances based on the measured variability of the dynamic characteristics over the samples. So, the idea is that the variability of the input parameters of the FE model, in general, they cannot be directly measured or known, but we can measure the variability of the dynamic characteristics associated with different samples by conducting model tests on those samples. So, therefore, we measure the variability of the dynamic characteristics, and then by an inverse procedure try to infer the variability of the input parameters of the model. And this process of inverse identification of the mean and variability of the input parameters of the FE model is referred as stochastic FE model updating. In this way, we come to the end of this lecture. So, in this lecture, we studied iterative model updating using model data, which is also referred as inverse eigensensitivity method. We looked at the formulation of the method, and we also looked at an example of iterative model updating using model data. We also briefly discussed what is stochastic FE model updating. Thank you.